Hello everybody, welcome. The aim of this screencast is to go through the calculator tutorial and show you how things work. Some of you might prefer a screencast to the tutorial as we have it on the website, so I want to offer you an alternative way to go through the initial tutorial into MPS. So what we're going to build here is a project that looks somewhat like this. Well, now I opened a sample that is bundled with MPS, so if you want to see the ultimate goal of our endeavor here, just open the calculator sample from the sample projects and you get to have the application done. So the application will allow us to define some wage calculators in which you specify input fields and output fields and expressions that should be used to calculate output using the input values, and when you run it you get a swing application form where you type in the number of hours and you get the calculated wage that you should charge. So this is the goal. And this is the beginning. I just started MPS and now we need to create a new project. So we're creating a new project in which so we'll give the project a name. So it will be stored in this folder. Now we'll create a new language as part of this project. Let's call it tutorial.calculator. And we'll create a new sandbox solution. So that will be a place where we can immediately start using the language. So not only we design a new language, but we'll also be able to use it. Okay, and here's our new empty project. On the left-hand side in the project panel, we see a logical view of our project structure. So we see there's one language called tutorial calculator and one sandbox solution called tutorial calculator.sandbox. In the sandbox solution, we see there's one model there. So this is the place where we can now write our code. And in the language, you see there are several aspects of language definition. So this is the place where we will be defining the language. Okay, and just following the instructions as they are written in the language tutorial, we'll now start designing the language first. During this screencast, I don't want to go into all the details because you can find a lot of explanation in the tutorial itself. So we'll go through it. I'll explain some things, but some things might be you might find some of the other things in the tutorial itself. To define a language, you have several aspects of that language that you can define. Structure is the one where you typically start because this is the place where you design the kinds of your nodes, the concepts. So we design a new concept that would represent the whole calculator form. So the form that within which you can then specify input fields and output fields. So we'll call it calculator. So now we have a concept called calculator, which extends base concept. Now calculators should have names so you can distinguish them. To give them a name, you implement inamed concept. So that's an interface that defines one property called name, some useful behavior, and MPS recognizes inamed concepts. It recognizes inamed concepts, so it knows the name in inamed concept has some special meaning, it's a name. Also, calculators can be roots, so they can be at the root of the AST. So they will not be hooked into code somewhere, but they will represent independent nodes, or you might think of them as files if you were editing in plain Java. Alright, well the next thing we need to define after having abstract structure is the editor, because we need to show our calculator on the screen somehow so that the developer can edit it. So we'll add a new editor. So here is the definition for the editor. So it's a special domain-specific language in which you lay out the content of the node on the screen. Now typically you start with square bracket minus, which introduces indented layout. So that's like the default choice for layout that is highly configurable. So let's use that one. And now within that layout we can place elements that represent properties or children of our concept. So how about just showing calculator as a string and then name of the calculator to the user? So we start typing calculator, it becomes a constant cell. So this is just a constant text or label on the screen. Hit enter. So you can add another cell. Now this time it will be the name property that we inherit from iNamed concept. So Control Space will open the drop down menu, and now we can search for name. Name is wrapped with curly braces. So here we go. So this is the one. So now we have an editor. Now, having abstract syntax and concrete syntax, we can already start using the language. So right-click on the language itself and choose Make Language. So that will prepare language for use. Alright, we're good to go. If you remember, I told you this solution is the place where we can experiment with our language. So inside the sandbox model, which you can think of as a package in Java source code structure, this is the place where we can now create new calculators. You know, for this to work, you have to have tutorial calculator listed among used languages in the properties of that model. So now when you go new calculator, you get a new empty calculator and you can give it a name. We can't do more, unfortunately, so let's add more functionality to the calculator. The first thing to add are the input fields. The calculator needs fields in which we can type in the hours we spend on different tasks. So an input field on the form will be represented by a new concept called input field. So we'll create a new concept. Give it a name, input field. Should be an iName concept, because input fields should be distinguished by their names, so they need to have names. This time, these are no longer root concepts, because they will be nested within calculators. And no additional properties nor children are currently needed. So time to define an editor for input field. So again, square bracket minus to get indented layout. We'll put a label input on the screen and then name next to it. So this is good enough for now. So we've got a new concept called input field and an editor for it, so now the developer can give it a name. The next task is to embed input fields in calculators. The calculator will have children. We'll give them a name, input field. They will be of type input field, and there will be 0 to n of them. So now each calculator has a collection of input fields hidden behind the input field child. And the editor needs to be updated so that we can see them on the screen. So now we get to the editor for calculator. And now being positioned at the name property, we hit Alt-Enter to invoke intentions. So that's pretty much to get whatever is hidden behind this bulb. But since clicking it by mouse is not very convenient, you have the keyboard shortcut Alt-Enter, very useful one. Well, the second most used one after Control Space, I would say. So you go Alt-Enter to get this pop-up and now add new line. So after name there will be a new line break. So all the elements, all the new cells will be on a new line. So this is the place where we will add input fields. So input field is an array of nodes of type input field. So they are wrapped inside a collection. Since we want each input field to be on a new line, we again hit Alt-Enter and select Add New Line for Children. So each input field will be on a separate line, because each input field is a new child of calculator. Now you might wonder, I hit this intention, nothing really happened. Well, that's right, because there are changes that you couldn't see so far. They are hidden in the inspector. Inspector is the window down here that you can open, and it gives you additional properties of each element that you select in the main editor window. So like for the input field collection, you see down here there's a property, indent layout, new line children, meaning all new children should be on new line. Identically for name, where we used the new line intention, you've got indent layout new line property set to true. So an alternative way to set these is to do it down here in the inspector. So if I do it again, click on a name, and you want a new line break after the name cell. So you jump down to the inspector, Alt 2 is the shortcut to get you there. And now you start typing indent layout new line. You add this property there, set it to true, and it will wrap the editor. So it will put a new line break right after this cell. So now we can compile again. Control F9 will do the job. And now getting back to the calculator, you see the editor is now different. Now we've got a place where we can add input fields. So if you hit enter, now you can add a new input field. So we add those that are defined in the tutorial, like this. Now we add output fields in exactly the same way. So we need a new concept. It's an output field base concept. This time we don't need to give it a name, because we don't want to refer to output fields, so they don't need names. So now the editor, just a constant output. Now we need to add them to calculator. And we need to update the editor for calculator. Children on a new line, and additionally we'll put a constant cell just to separate visually input fields and output fields, and new line there. Control F9 to compile, and switching to my calculator, now I can enter output fields. The output field at the moment is not very useful, is it? So what we need is to add an expression to an output field, where we could type a formula that will get calculated. Base language in MPS has already expressions. There's a concept in MPS called expression, which is a root of many kinds of expressions in base language, like assignments, method calls, variable references, binary operations, and so on and so forth. So we need to take expression, make it part of our output field. So in the output field, we need a new child. It's going to be an expression and we're going to have exactly one. So our output field now has one child of type expression, and we need to add it to the editor as well. So in the editor, next to the output, we'll add the expression. Now expression knows how to render itself, so we don't have to go into detail. So depending on the actual type of the expression, it will be rendered correctly without any extra effort on our side. So if we rebuild and get back to calculator, So when we get back to calculator, we see, well, this is red, and we can't really type anything in there. So the expression can't be edited. Why is that? Well, that's because we don't have base language added to our model. So now we need to take properties of our model and say we're using base language. So we need to add base language to the list of used languages so we can use it in our model. So now if we type a value 10, we have it there, or 2 plus 3 plus 5, whatever expression you can think of. We can do that. Now the downside is we can't refer to the input fields that are up here, so we can't add references. So that's what we need to do next. So we need an input field reference, a new concept, the sole purpose of which is to refer to input fields. So new concept, input field reference. Now this time it needs to be an expression because we want to embed it in the expression part of an output field. Expression. Now we get an error. We are not extending base language, yet we are trying to build concepts that extend concepts from base language. So our language, our calculator language, needs to extend base language. Here's a handy intention to do it quickly, so it will just add base language to the list of extended languages, or we can do it manually by right-clicking on the language, picking properties, and among dependencies, we'll add base language. And we make it to be the language we extend. So this is important to do this way. So now when we get back to the editor, now the error disappears. If it doesn't, then hit F5 to refresh. So it will rerun all the checks, and then it will be discovered that base language is already extended. I didn't have to. Back to input field reference. So input field reference needs to refer to an input field. So in the reference section, we create a new reference. So new reference, field, called field, now referring to an input field, exactly one input field. The editor. So now in the editor, we'll just add field. So this is a reference. So instead of showing any extra arbitrary node, we just show directly the target of the reference, which is an input field, but we won't show it in its entirety, but only part of it. So in our case, only the name. So the reference will be on the screen in the editor represented by the name of the field it refers to, so that it looks natural. You will see the same name that the definition of the input field has. Although you could make it look different if you wanted, but typically in languages that are commonplace, this is the way references are represented. So after rebuild, you go back to the calculator, and now Control Space will reveal a list of input fields we can put in. So we can select width. And not only we can put it there, we can navigate to definition by Control B, and it will get us to the place where the input field is being defined. Or we can hit Alt F7 to search for usages, and it will find places where that guy is being used. Or Control Shift F7 will just highlight the usages, and F3 will let you navigate around the screen to see all usages of that input field. So you get all this for free. Well, this still hasn't been much fun, was it? Well, we couldn't run the code. No, so it's time to change it. So now we need to define a generator that will take the calculator definition as you see it on the screen and turn it into runnable Java code. So to do that, we need to address the generator aspect of our language. So we already have a generator, and in the generator we have single mapping configuration. So currently it's an empty generator which doesn't generate anything. But now we have to specify rules that will turn our calculator into a Java Swing form. Since the generator in MPS is based on model-to-model transformation, where you using the target language, you specify a template which you parameterize with values from the input model. So we need to create a template that will represent the outcome, the resulting Swing application. And then we'll tweak it with values from the form, from the calculator, so that it does what the developer intended. So we start with creating a new class in the generator, because we are generating into base language class. So as an input for this transformation, we take the calculator. We give the class a name, which is irrelevant in the long term. So in mapping configuration, in the root mapping rules, we add a new rule that will translate calculators into some base language classes using the template that we name here. So this is the template that will be used for translation. Now we can rebuild, Ctrl F9, and looking back at the calculator, we can preview generated text to see what gets generated. Well, it's an empty calculator implementation class, so we are definitely on the right path. We are able to generate an empty Java class out of our calculator form. We'll now change the name of the class so that it reflects the name of the calculator. You know, in the calculator here, we say it should be named somehow. So we would like to use the same name here. So whatever the name of the calculator was given, whatever name was given to the calculator, we want that name to be used in the generated Java class. The generator provides several macros you can use to parameterize the code in your templates. One way is to select the name, hit Alt-Enter, and now in the menu pick the right macro. So the property macro is the one to use. So we'll hit that one, and now the inspector opened. You know, remember the inspector, the thing down here, or Alt-2. And in there, you now type the code that will retrieve the property or the value that should be given, that should replace whatever has been put in the macro. So instead of calculator implementation that we have up here, what we want is some other string. You might type in anything you like, but that's still not quite it. Instead, we want to take stuff from we want to take a value from calculator, which can be referred to as node in here. So node is the calculator, the input in the input model. So we have a calculator. Now that calculator has a name, and that's what we want to get. You know, this is the name given to the calculator, and this will replace, well, the string that's wrapped by property macro. So if we rebuild and look at the generated code, now you see that the name of the generated class is the same as the name given to the calculator. Now back to the template. We would love to have some Swing components added to a frame so that we can really generate a visual application. We need to have a public static void main method. Well, in that method we want to call Swing utilities, but this package is not available, so we have to import it. Well, for this we need the properties of the generator model, and in the dependencies section we add packages that we will depend on. So it's javax.swing. Okay, so here they are all. Hit OK. And getting back to the generator, we should be able to complete the code. So Swing utilities. And now we'll enter the code as described in the tutorial. Now you see how fast I can type, right? So now we're in the middle. Now we need a constructor. Now, with all the code in place, we can start parameterizing the template. Well, the first and simple thing, calculator, could be just, the title of the frame could be identical to the name of the calculator. So, once again, Alt-Enter, property macro, and now to make it quick, we just use the pre-prepared property macro. As expected, this will add node.name in the inspector for the property macro. Now, finally, the generator becomes quite exciting, because we need to add, for all input fields in the calculator form, we need to add a Java field into calculator implementation template. So we'll make a private JText field. We call it input field. So now we have a field, and we initialize that field to a new JText field. Good. So we've got an input field now, a JText field, a swing component to represent an input field. What we need to do, we need to generate these for each input field in the calculator form. So we select the whole statement, including the semicolon. So now, Alt-Enter, we get a list of options. We'll pick node macro. And out of the many node macros available, we'll choose loop. Since we want to loop over all input fields in the calculator form. Calculator is the current node, and input field is the name, is the child representing all input fields. Remember, back in the calculator structure, this is the input field that we refer to. So now we loop over all input fields, and for each of them we create a dedicated JText field. Since we'll have many of these in our Java class, we need to give them different names, unique names ideally. So we'll no longer call them input field, but we'll use a property macro. So we'll use a property macro to give them unique names. So now the name to give to the input field will come from the generator context, which is capable of generating unique names. We give them just some common base. In our case, could be input field. So now the name will be, for each input field, the name will be different. Now we need to do the same thing for output fields. So I select the statement and duplicate it. Now, obviously, now we need to iterate over output fields, not input fields. To make the model valid, we need to change the name here. And for the property macro, we'll also use a different base for unique names. So that should be enough to have fields for input fields and output fields generated into the form. Let's have a look. So now back to the calculator, preview generated text. Now we see that we have 3 input fields, 1 output field. They really have unique names, plus we have all the code that we wanted, and the title of the form is customized as well. So it all works as expected. Well, in the following step, we'll add input fields to the form. So in the constructor, now we'll add a block statement. So block statement is basically a nested block of statements, and we use it so that we can repeat that block statement several times for each input field. You'll see shortly why this is needed. Without block statement, we wouldn't really be able to put in a loop macro. So we'll add a document listener first to the field. We'll add a new label. with some title, and we add the input field. Now, since we have this code in the block statement, we can select it as one unit, as one block, and add a loop macro around it. And again, we'll be looping over nodes input fields. And the label shouldn't say title, but it should say the name of the input field. So we'll use a property macro, well, the one referring to node name. But here node is not a calculator, but an input field, unlike in the loop. You know, in the loop, the node refers to the calculator. If you hit Ctrl-Shift-T, you get a type dialog in which you see that we're looking at a node for a calculator concept, while inside the property macro, we are inside the loop. So the local node inside the loop, here, this guy, is an input field. So it's a node referring to an input field. Now, looking inside this loop, what is this input field? You know, how do we attach this input field with the one from here? So here we create input fields for each input field in the calculator, and here we're supposed to add visual elements to them. But how do we get them? How do we get the one that's appropriate for the current input field that we iterate over? So we need to put a reference that would recall the correct visual JText field from somewhere, the one that corresponds to the input field that we currently iterate over. For tasks like this, we need mapping labels. Essentially, what we need is some sort of mapping between calculator input fields and JText fields, so that if we hold a node of the input field, so if we hold a node coming from the input model, an input field, we will get back the JText field that corresponds to it. The mapping configuration is the place to start. We need to add a mapping label. So that's exactly such a mapping between concepts from the input and output models. So let's give the label a name. Input field declaration would work fine. And it will map from input field, which is our concept nested in a calculator, to field declaration. And field declaration is coming from base language, so it's a declaration of a field inside a Java class. So exactly the node wrapped here. You know, if you visualize, this is field declaration. So in the inspector down here, you see this is field declaration. So that's what we want to get. Well, and to add stuff into the mapping label. So to add elements into this mapping label, we mentioned the mapping label in the mapping label section of the corresponding loop macro. So here we add our field declaration. So now the loop macro will keep adding the generated generated field declarations into the map. Well, and now here input field will not be a real input field, but will be replaced with a reference macro. And the reference macro would search the mapping label for the correct field declaration. So we'll again ask get generator context for help. We'll get output by label and input. So the label is the only one we have at the moment. Well, and the key into that map will be the current node. So the input field that we currently iterate over using the loop macro. So the loop macro takes all input fields. So the current one, so we iterate over all input fields. So the current input field is the one that we can refer to as node. Again, just a quick check. It is an input field. So that input field we use as a key to retrieve the corresponding field declaration from it. So that field declaration will replace this guy. So then we can call get document and add document listener on it. And similarly, we need to update this reference. Now, if we compile and look at what gets generated, so we have text fields, and we have code that adds correctly listeners and labels to the fields and adds those fields to the frame for all 3 input fields. So this works beautifully. Now the same thing for output fields. So we need a block statement in which we add new JLabel, and we add an output field, we iterate over output fields. Now we need another label, output field declaration, which would map output fields to field declarations. Well, and this loop will fill in the values, and here we're gonna collect them in a reference macro. Generate a context, get output by label and input, and the input is the node, the output field that we're currently iterating over. Okay, well, the final step is to calculate values for the output fields using values from the input fields. Just as they say in the tutorial, we need to change the update method so that it looks somewhat like this, but for all the input for all the output fields. So you need to parse values from input fields, store them in variables, and then for each output field just enter the output field dot set text, and now in the set text method you provide an expression that calculates the correct value. So now this is the code that will generate. So we go to the update method, and first we need to create an integer variable that will store value, a parsed value from an input field, from each input field. So for each input field we need a local variable. So let's start with 1 int I equals 0, and we make it a loop. Across input fields. Now for each variable we need a unique name, otherwise we'll have collisions, right? They can't be all called I. So let's do a property macro, and we'll use generator context to give us unique names, starting with the string I. And now we need to store these variables again in a mapping label so that later on we can retrieve them. So again we need a place to store them. So back to main configuration and another mapping label, local variable, which is gonna map input fields to local variable declarations. So now we select local variable declaration, so just this part, not this one, this would be the whole statement. Now we need just the variable declaration, and we'll wrap it with a map source map source macro. So this macro will effectively just store this local variable declaration in the mapping label. So in local var, we store the current source node. Okay, well that's it. Now, to initialize the fields, we only have declaration, but now we have to give them the values from the corresponding input field. So we need to parse the values that are in the input field. So let's write a try catch block to catch for number format exceptions. So within here we can now parse the input field getText and store it in the local variable. So I equals integer parse integer, and now the value comes from an input field getText. Now this whole thing needs to be generated for every input field. So again, a loop macro, loop on input fields, and the variable that gets initialized must be retrieved from the local var mapping label. You probably get the pattern, right? Here we store them, and since here we need them, we retrieve them from the mapping label. So again, a reference macro, generate a context get from label using the input node, using the node which is the input field. Well, and the input field also needs to be retrieved. So this input field here is also retrieved using our reference macro. So now we need to ask generate a context. So we need generate a context get from the input field label, again by the current input field. So for each input field we now retrieve the corresponding local variable and initialize it with a value from the corresponding text field. Now it's time to handle output fields, isn't it? So output field, we need to set text to whatever gets calculated. Well, we don't know yet the result, so let's use null as a placeholder for the moment. Now we might have more than one output field, right? So we need to get them all. So we'll iterate over all calculators output fields so that this line is generated for each of them. And the output field itself needs to be a reference to the generator context, to the output field label for the current node. So currently we hold the output field, so we go to output field declaration to get the field declaration out of it. So now we have it, so we can set its text to something. Now that something is the expression. So the expression needs to be placed in here, and it needs to be calculated. The expression will be an integer, so to turn it into a string, probably the easiest way is just to add an empty string in front of it, and then replace this null with something real. But now, so we want to replace null with the expression that is part of the output field, so the computation. But we also want to have it wrapped inside parentheses, otherwise it would just be concatenated to the empty string. So now, once we are, now notice I used the surround with intention, Control-Alt-T or Command-Alt-T, surround with parentheses. So now null is surrounded. Now I can select it and pick the copy source macro. Copy source macro is a macro that will replace whatever it's wrapping, null, with whatever is specified here. So the map node.expression. So the expression will, whatever node expression gets generated into, will be put instead of the null value here. Now there's only one case that we still can't handle. Do you know which one? We still can't handle references. So we still don't know how to handle those. a reference from here to an input field, but we don't know what to generate it into. So that's the only remaining piece which we need to define now. So back to the mapping configuration. So we need to specify a reduction rule that will replace an input field reference into something that's valid in base language. So an input field reference needs to be translated into something. So we'll use an inline template because this is going to be very short. Inline template with context is exactly what we need here. So first we need to build some context. Block statement is exactly what we need here. And in that context we need some local variable declaration that we can use, so we can refer to it. So now we have a variable I, and now here we refer to it. Now this becomes the template fragment. So this reference to local variable I becomes a template fragment, and we'll use a reference macro to make it point to the local variable generated for the corresponding input field. So now we'll add a reference macro, which and now the target of it we retrieve from generator context. So get output by label. So we get a local variable declaration for the input field. Well, the input field is what? Well, it's the field that the reference in the input model refers to. So node is an input field reference, so it's pointing to some input field. So we now need to know what that input field got translated into. So that field. So now we get the JText field that this input field was generated into. So we recompile. And looking at the calculator, here is what gets generated. Well, it looks like what we wanted. We've got input fields. We have them all initialized. We've got output field. We have that output field added to the form. We have an update method which has local variable for each input field. Each is initialized with a value from the corresponding input field, and then the output field has its value set to the expression we added, including the reference that we had. Reference pointing to the to the local variable that stores the value of the first input field. Now you can imagine you could take this generated.java file, point your favorite ID to it, and compile it, run it. However, it wouldn't be complete for me if I couldn't see my code running really right here in MPS. So now I'll show you something that's not in the tutorial. I'll show you how to make this run. In order to make MPS to recognize that your calculator concepts are runnable, so that then you can just click on such a node in a tree and run it, well, you have to implement the iMain class concept. Well, it's not imported by default, so you need to use Control R to import model that contains that root, iMain class. So this is the one. So we effectively need to depend on JetBrains MPS execution util. So now we have it, but we need to extend it. It's not being extended now. It's not being extended, so we need to extend it. With a quick fix, we make it so. So we can double check. In dependencies, we see execution util extends. Perfect. So we extend it. So now after rebuild, by the way, I was using the Control-Shift-A command. If you don't know that one, learn it. I think it's the most useful shortcut in MPS. Control-Shift-A, execute command by name. Or you could always rebuild the project from the build menu. And now looking at the calculator, hey, here we go. So we can run it or debug it right from MPS. Here's the form, and when you start typing, you get the value properly calculate it. Okay, that's all for now. Thanks for watching, and if you're interested, watch the second part where we talk about type system and scoping. Bye.